Now I can discuss a more important and interesting application of the improved Shiraishi-Saito inequality, namely the trade-off relation between power and efficiency of a heat engine. This is based on our joint work back in 2016. And I said it was a recent work, but I found that it's already 7 years ago. And probably it's much older for you watching this video. Okay, so anyway, let me start by explaining you the motivation about efficiency and power of a heat engine. And I believe that all of you know about heat engine, more precisely an external combustion heat engine. This appears in any textbook of thermodynamics. So a heat engine is a thermodynamic machine or a thermodynamic process that operates between two heat paths, one with higher temperature and one with lower temperature. And it usually operates in a cyclic manner. And within a single cycle, it absorbs heat QH from this hotter heat path, and it expels heat QL to this colder heat path. Since the energy is conserved, this difference W is extracted as useful work, and we can, for example, generate electricity by using this work. And of course, you want this W to be bigger. And there are two characterization for a heat engine, and you want both the characterization to be high. And one very standard characterization is the efficiency. It's simply the W, the extracted work divided by QH. If there's no second law, and if we only have the first law, then W may be equal to QH. In that case, this efficiency is 1. It means that we can make use of all the energy that we absorbed from heat path. But as you know, there is something called Carnot's theorem, which is one form of the second law in modern thermodynamics, that tells you that this efficiency can never exceed this universal constant, which is called the Carnot efficiency. Okay, and it's given by 1 minus beta h over beta L, and this is always strictly less than 1. And so whatever engine, how clever you are, you can never design an engine whose efficiency is higher than this Carnot efficiency. This is a universal upper bound. But the efficiency is not the only measure of a good heat engine. You also want, if you want to make use of your engine, you want to have higher power. Okay, the power is by definition the extracted energy divided by tau naught, which is the period of the cycle. Okay. But unlike the efficiency, there is no fundamental limitation on the power of a heat engine. So we want to have a heat engine with high efficiency and high power. And the question is there any limitation for this power? Okay, so let's look at examples. And one obvious canonical example of a heat engine is Carnot cycle. And I don't explain Carnot cycle to you, but I think all of you know that Carnot cycle attains the maximum efficiency eta c. But any Carnot cycle is realized only in the quasi-static limit where the period tau naught diverges. And then since W is finite and tau naught is infinite, this power is vanishing. It's just 0. So it's a very efficient engine. It has the maximum efficiency that we can desire, but it has the smallest power that we can think about. It has 0 power. So this is totally useless. So let's think about something else. And well, so as a starting point, we can think about perturbing a little bit about to the Carnot cycle and consider something that I call near Carnot cycle. Okay, so and I want to somehow speed up the Carnot cycle. So why was Carnot cycle so slow? Well, for example, this is near Carnot cycle, but in Carnot cycle, you have an isothermal process in which the temperature of the bath, the temperature of the bath and the temperature of the engine is exactly the same. That's quasi-static isothermal. And in this condition, we want to transfer heat QH from the bath to the engine. But since the temperature are exactly the same, the heat flow is infinitesimally small, and it takes infinitely long time to transfer some amount of heat. So in order to speed up heat transfer, I assume that there is small temperature difference between the engine and the bath. And so delta beta is some positive quantity. So this means that the temperature of the engine is slightly lower than that of the bath. And then there is some finite current. So this process does not require infinite amount of time. And here we have a adiabatic process. And here, this is the second isothermal or near isothermal process. Okay, so again, we make some small temperature difference between here and here to encourage this finite heat current. And again, adiabatic process. So then what is the efficiency, maximum possible efficiency of this kind of near Carnot cycle? Well, it's easy. You can think of this as almost Carnot cycle with slightly different temperature than the original. So if you recall, this is the Carnot efficiency. And these are the temperatures of the bath and also the system. But now in this case, the system or the engine has slightly different temperatures. So we plug in these temperatures to the formula of Carnot efficiency. And it's quite reasonable that this eta is roughly the efficiency of this near Carnot cycle. Okay, and I assume that this delta beta is small and expand to get this. So now I see that the efficiency of this thing is slightly smaller than the Carnot efficiency. Okay, now I ask, what is the period, the minimum period required for this near Carnot cycle? Okay, as I said, the important processes that are these these isothermal process or near isothermal processes. So I will consider the time you needed to require this heat transfer. And so since in total we want to transfer heat QH plus QL, and I didn't say this. And I assume that induced heat current is given by some constant times the temperature difference, like this. So this K is some constant which depend on the material and how you make contact between the engine and the heat bath. But anyway, this is something related to thermal conductivity. Okay, so I assume that there is such constant. Then okay, so this is a minimum period of time. You want to transfer this amount of heat, and this is heat current. But since J is given by this, we can rewrite it like this. And now here in this formula and in this formula, we have delta beta. Okay, so we can eliminate delta beta and combine these two relations to get the final relation here. This combines the period and this heat absorbed or expelled by the engine and Carnot efficiency and the efficiency of this near Carnot cycle. Here we have a material-dependent constant K. Okay, but anyway, if you look at then K is of course finite, and if you look at this, and then recall that we want to have an engine with high efficiency. And of course, eta cannot exceed eta C, so you want it to be as close as possible to eta C. But you see, if eta approaches eta C from below, this converges to 0. This approaches 0, and we have inverse. So this means that tau 0 diverges. Okay, what does it mean? Well, so yeah, so this is a question and main conclusion. So we observe that as efficiency eta approaches the Carnot cycle, this tau naught diverges. This means that power must vanish because these are finite and this diverges. So our conclusion is that within this near Carnot cycle, there is a kind of trade-off relation. If you want to make the efficiency higher, if you want to make your efficiency close to eta C, then your power becomes smaller and smaller. Okay, so now, but this is just one example, very easy example, which was very close to Carnot cycle. So our main question is this a general or inevitable feature of heat engine? And actually, our answer is yes. We prove a universal bound. So in this case, we are only treating very simple example, but we treat any heat engine, which can be arbitrarily far from equilibrium. It can be very, very, very non-equilibrium, and it can do whatever you want, you can imagine or you cannot imagine. But we will show that there is this kind of trade-off relation. So a very related question is, are there heat engines with non-zero power that attains the Carnot efficiency? Okay, we know that the Carnot cycle attains the Carnot efficiency, but it has zero power. So the question is there a dream machine which has non-zero power and also attains the Carnot efficiency? But unfortunately, our answer is no. Okay, and the punchline of this work is that there exists an inevitable loss, dissipation, when the engine exchanges heat with the bath, and this leads to this trade-off relation. And I would say that I will comment on this again, but I would say that this is a fundamental limitation of external combustion heat engines. Okay, and as you can guess, the improved Shiraisi-Saito bound says that whenever you have current, you get some dissipation, you get some loss. So the inequality is perfectly suitable for deriving this kind of result. Okay, now let's go into the theory. So here is our mathematical setting. So again, we consider a Markov jump process. Okay, and we can generalize this to much more realistic systems. But anyway, here we only consider Markov jump process. So here we consider a process, a system, which is engine in touch with two heat baths with we call H and L, of course, with high temperature and low temperature. And we consider an arbitrary Markov jump process described by the transition rate and this energy for each state. And we assume that this time dependence is determined by some fixed protocol. Okay, and I say this protocol may be periodic in T. This is confusing. If you consider the standard heat engine, of course, it operates in a periodic manner. So it's very natural to consider a protocol which is periodic in time. But actually, that's not mandatory. So you don't have to have periodic protocol. And I will tell you the precise assumption that we need. So we can basically consider any protocol, okay? And our main assumption is, of course, the local detail balance condition, which says that this ratio is given by this. Now beta depends on the jump, okay? So for each pair JK, alpha can be either H or L. Again, this means that when jump from J to K or K to J take place, either H or one of the two heat baths is relevant, okay, as before. And this is our master equation. Okay, an important quantity is the heat current to bath. And this is almost the heat current that we have been considering all the time. But this J from J to K is given by this energy difference when this alpha JK is alpha, and it's zero otherwise. So if this is H, this of course tells you the heat current into here, and if this is L, it describes this heat current. And the entropy production in the bath is from this relation, from this, it's given by this as usual, and by using this, it can be written like this, okay? Everything is standard. Okay, now we will focus on averaged quantity because it's most useful and it's easy to treat. Okay, so here is our assumption. We assume that the following limits exist and are positive. And these are simply the averaged currents. But since we want to treat this kind of heat engine type setting, we wanted to use this heat engine sign convention. So this JH is heat current from the system to the bath, engine to the bath. But we want to consider this transfer of heat. So I will denote by Q of H the minus of this time average of heat from the engine to the bath. And I assume that this limit exists, and it's this one, the whole thing is positive. So heat goes in this direction, and QL is QL, of course, denotes the time average of this heat current. Okay, and the existence of limit is guaranteed when the protocol is periodic in time, but that is not the only case where you have the limit. So our assumption is only this. So the limits exist, and they have this sign. Now, of course, this sign is mean that we design some heat bath. No, heat engine. Then, of course, they must have this sign. And then this W is the average power. Yes. And this eta is the efficiency or averaged efficiency, W divided by QH. And now let's look at corresponding time average of the entropy production in the bath. So this is the definition. And since entropy production is given by this, the time average is simply given by, so be careful of this minus sign. So the time average is simply given by this. Okay, so I'm trying to write everything in terms of sort of more thermodynamic quantity or more heat engine-like quantities. And this is just the consequence of the definition. But let's recall that this QL, QHW are related by this. So I plug in, I substitute the QL equals QH minus W to here to rewrite this like this. And now you rewrite this like this. You divide everything by beta LQH and write it like this. Then, rather interestingly, here you get this, and here you get 1, and here you get this. Now look, this is nothing but the Carnot efficiency. Okay. And this is nothing but the efficiency of this engine, this whatever. This is a very, this describes a very arbitrary engine, which can be very, very, very far from equilibrium, or can be very close to equilibrium. But anyway, this is the efficiency of our engine. Okay, so rather interestingly, this entropy production can be simply written like this. So what does this mean? This means that when eta, the efficiency of this engine is close to eta C, the Carnot efficiency, then this averaged entropy production in the bath vanishes. Okay, this is very interesting. So this measures a kind of loss or dissipation. And so this means that whenever you have dissipation, your efficiency differs from the Carnot efficiency. So your efficiency can be equal to Carnot efficiency only when you don't have any dissipation, any loss. Okay, now we are almost done. And the only thing we can now apply the time average Shiraisi-Sato inequality after choosing our G. Here we choose our G like this, but this is very natural because we want to consider this setting here, and the average of quantity is given by this. So actually, you easily see that the average of this is nothing but QL plus QH. That is the very natural quantity that we want to look at. Oh, it's here. So this is the time average Shiraisi-Sato inequality. It's in page 25, but I don't mean there is no need for looking at page 25. It's here. Okay. So this left-hand side, we have the time average of this quantity. So as I said, it's precisely QH plus QL squared. On the right-hand side, we have this constant Xi, G, I omitted G, Xi bar, and this is the time average of the entropy production in the bath. So we have already seen that this can be written compactly like this. And what is this Xi bar here? In this case, it's a very simple quantity like this. Okay, so look, if you don't have this square, this is simply the time average of heat currents. So we have squared. This means that this is a very natural meaningful quantity, which tells you how actively the system exchanges heat with the bath. Okay, if you have this, it's heat current, so it has direction sign. But we have squared, so this just measures the activity of heat exchange. Okay, so it may have a good name. So it's a very natural quantity, which of course depends on the design of the system, of the stochastic process. And okay, so anyway, putting everything together from this time average Shiraisi-Sato inequality, we get this bond. And I stress that this is an inequality between thermodynamic quantities and this system-dependent natural constant Xi bar. And we only have QH, QL, beta L, QH eta, and this is Carnot efficiency. Everything, you can show this equation to like Carnot. So this does not contain any difficult quantities. So actually, this is related to my remark that I made when we derived time average Rice cycle inequality. Probably you remember that I emphasized that the Shannon entropy SPT dropped out from our inequality. Of course, we had the Shannon entropy in non-time average version of Rice cycle inequality. But when we performed time average, this S disappeared from our theory. And I said it was a nice thing, right? And suppose that we had S in this kind of bound, then we have to say, oh, here we have information theoretic quantity S. How do you evaluate this S? You have to know the probability distribution and so on. Of course, if you're very close to thermal equilibrium, then S may be close to thermodynamic entropy. But in general, we are treating a very, very, very non-equilibrium process. And then in that case, Shannon entropy almost does not have any physical meaning. This may be too strong, but that's what I think. Okay, so a theory with something like Shannon very microscopic quantity like Shannon entropy has weakness in application. But look, our inequality only has thermodynamic quantities. That's one thing very nice about this. And here is another nice thing about our inequality. Recall that we analyzed something that I call near Carnot cycle in page 30. And this is page 30, and we derived this relation. Now, think about dividing everything by tau naught and rewriting this in terms of the time averaged quantities. So that's what we did here. So believe me, this is exactly the same equality, but I used this QH, which is defined like this, and QL defined like this. And then we have this relation for near Carnot cycle, and look, they look exactly the same. And moreover, you can show that when the system is very close to equilibrium, and then in the first order in non-equilibrium, in the first order of non-equilibrium, our Xi, this quantity is exactly equal to K, which is related to thermal conductivity. Okay, so what does it mean? This means that our inequality becomes exact or saturated for near Carnot cycle near equilibrium. And this means that our inequality is optimal. You can never improve this. Now we can discuss the consequence of this inequality about efficiency and power. So this is our main inequality. So first of all, to see the implication, let's rewrite this like this. So now we have all Q's here, and this is a finite constant related to heat conductivity, and this is inverse temperature, and this is eta C minus the efficiency of our heat engine. And so suppose that the efficiency of our heat engine becomes closer and closer to the Carnot efficiency. And then this approaches to 0, but we have this on the right-hand side, or this is further lower bounded by this, right? And they are non-negative. This means that when eta approaches eta C, both QH and QL should approach 0. And of course, the difference W, the power also goes to 0. So the power must vanish when eta attains the maximum Carnot efficiency. Or if you want to have a more explicit bound for the work, then for the power, then what you want to do is rewrite this like this. So you bring this here, so you only have 1, but you multiply both sides with W like this to get this, right? And then you recall that W is eta times QH, so you have QH squared. So you get this upper bound. W is upper bounded by this constant beta L, something like with heat, and eta times eta C minus eta. Okay, and again, this is an optimal bound, which is saturated for near Carnot cycle. Okay? But this, if you want to have a simpler form, then this is not an optimal inequality, but you can upper bound this term by 1, so you get you can upper bound the power by this combination. It's a very simple, nice inequality, neat inequality. So this is the inequality that we show in our paper. And this of course says that when efficiency eta approaches eta CW, the power should vanish. So an engine with high power inevitably has low efficiency eta. Okay, so I like to stress that the bounds are universal in the sense that they apply to any heat applied. They apply to any heat engine that we can design any complicated heat engine within our theory, and it can be in state very close to equilibrium or very, very, very far from equilibrium. It can be rather very arbitrary, or the heat and the engine may be small or maybe large. It can be macroscopic usual thermodynamic system. Whatever engine you design, our bound is valid. But we have to stress that this constant psi bar is related to the activity of heat exchange between the system and the bath, and it's just system dependent. It depends on the design of your system. What is the material you use? What is your material? How do you contact the heat engine and the bath and so on? So of course you can improve. You can improve the power of the engine by designing the system carefully to have a larger psi bar. That is of course possible. This is not the universal part. Okay, and we only discussed Markov jump process, but we can extend the result to something called Cramer's equation, which is more realistic. We discussed this we did not discuss extension, but we discussed Cramer's equation in part 5. And so this is the punchline that I already said. So the essence of our theory is that there is an inevitable dissipation loss associated with heat current between the engine and the heat bath. So this tells you that this is the fundamental limitation of external combustion heat engines, where you have heat source outside the engine. And so here it's explosion or fire or whatever, and inside you have working material. And in contrast, an internal combustion engine, in case of internal combustion engine, this is inside of the engine, and there is some explosion or something. And then in this case, you don't have to transfer heat from this heat source to the engine. So in internal combustion engine, we don't have any such limitation. So I think that is the reason that we use internal combustion engines like in our car. So I just took this picture. This is the engine of my small Toyota car. Okay. So this is basically all I wanted to say about the trade-off relation between power and efficiency.